So hello, welcome to my new video in which I'll be discussing about our sessional project, which is on a steel project, that is a design of an industrial building on STAT, as well as some manual calculations. So let's straight away get back to our problem statement. So this is our problem statement. Okay, design and draw the structural details for a steel industrial building. Okay, this is in factory shed, and this is a typical frame consisting of a truss, column, gantry rails, gantry girders, along with concrete footings. Okay, remember this is a concrete footing. So now our main objective is to design up to wind load of this truss. Okay, this truss columns we will be adding, but we'll just be giving the section, but mainly the wind load we'll be calculating for this truss. Now how this is, now let me tell you that for this we'll be requiring two codes, that is IS 800 2007 of which deals with limit state method, and the second one is IS 875 part 3 2015 which deals with wind load. Okay, I'll write here wind load. So this two, keep it in hand or download it, because you will need to check your values, okay, for a particular given data. And IS 875 part 1 and part 2, that is dead load and live load, it's not required now for our sake, okay, because sir has set us to submit it till wind load. So up to that, this two loads, this one are enough. Okay, so let's come back to this. So this is a total building, okay, factory shed, one frame, this is a truss, again truss, this is an again a different truss. So these are the symmetric. Okay, so if we design one truss or one frame, so they will be repeated. Okay, they will be repeated, which is at a certain spacing s. Okay, so here just we are taking one frame which is shown here. So we'll be just doing for one single frame and truss, and that will be repeated over the whole spacing. So this is the span of the truss, this is the span of the truss, okay, and this is the spacing between each frame or truss, you could say, which is denoted by s. L and s are given in our data sheet. Okay, so this is the data sheet. So for my roll number, I have spacing as 5 meter and capital H is 8 meter. I'll say what is capital H. Okay, so other details are not required for now. And span L is 18 meter for me. The location is Kanyakumari with pitch angle 21 degree. Okay, so let's get back to our problem sheet. So this is capital H, that is the distance from ground level. See here, it's from ground level, the distance from ground level up to this base of the truss. This is the called as tie. So up to the roof of the tie, this is the capital H. Okay, but this footing is extended up to 0.6 meter. Okay, this is extended up to 0.6 meter. So the effective, this is the steel length, so this will be h minus 0.6. I will show it in the PPT. So this is capital H for me, which is given as mm, 8 meters. So this length, this steel length will be h minus 0.6. Okay, so this will be 7.4. 8 minus 0.6, which will be 7.4. Okay, so before going into the stat portion, let me give you a brief about the truss. Okay, what are the different members? So this is a triangular member, you can see. The lower members are tie, which takes tension. This upper portion, let me go with the laser light. This bottom one is tie, which takes tension. The upper part is rafter, okay, which takes compressive force. And all, as we all know that the truss members only takes axial forces. Now, this is the central tie, and this is used to prevent the sagging or the deflection of this tie member. Okay, so this is all. This also takes tension. Now, this this part inclined portion is the major sling, because major means it's in longer length, so it's called as major sling, and it also takes tension forces. These are the minor slings. Okay, these are the minor slings. They also take tensions, but due to its less length, they are termed as minor. Now, struts. As we know, the tension members are called as ties. Similarly, compression members, the second name of compression member are struts. Okay, struts. So the major struts are this one, right? This, because these are of greater length. Therefore, this and this is the major strut, and the minor strut is this one. So struts take compressive forces. Okay. Now for minor sling, we will be taking ISA. Okay, ISA means Indian Standard Angled Section, single angle. If it's just one ISA, it's single angle. That means only one portion of this, not the double portion. Only the single portion will be shown here. For major sling, this also takes tension under dead load and live load. We'll be taking two Indian Standard Angle section. This is this one, and other is this one. What does this 75, 75, and 8 depicts? 8 depicts the thickness of the section. Okay, 75 and 75 depicts the length. There is this length is 75, this length is 75, and in middle this is joined by gusset plate. So gusset plate is of, we are taking it as of 10 mm thickness. So our sections should be less than or equal to 10 mm thickness. It should not be greater than that. Okay. I'm not going into details why it should not be that, because I want to keep it as concise as possible. So just see here, for minor sling also we are considering thickness as 6. For major sling it is 8. We can go up to 10, no problem, but not beyond 10. Okay. So two angled section or two eye section or two channel sections can be brought together with the help of a gusset plate. Okay, so let's come out of this. Okay, so this was all about here. Now let's go back to our problem statement. Now this is the straight line. So this is the pitch angle. Okay, the pitch angle is given in the problem statement. The problem state, sorry, in the data sheet we have our pitch angle. I have given, for me it is given as 21 degrees. So rise is not given. I have just written it here, but rise in our problem statement is not given. We have to calculate it by simple geometry. I will tell it further in the upcoming part. So the top part is called as ridge. Okay, this is the ridge. This is the whole span, okay, which has been given to us. For me it's, I have just written here 16 meter, some random values. For me it's 18 meter according to data. So pitch of the truss, that is P. Okay, this rise is to span ratio, that is 4 is to 16. But pitch angle is something different, which is tan of theta, that is this triangle. If we are considering this triangle, so it will be rise by span by 2. Okay, because this will be L by 2, so it will be nothing but 2 by P, because P is rise is to span, so tan theta will be 2P. Okay, so this is about that. And now let's come back to the calculation of no, let's go back to this. Let's complete the calculation itself first, then we'll go to the stat modeling. Now for calculation of this length of the rafter, first this height rise we can get as, we have theta, we have L by 2, so rise is equal to L by 2 tan theta. Okay, for me I was getting around 3.844. So this height is 7.4, excluding this 0.6, 7.4. Okay, so let me draw with some things. Not so this portion was, for me it was 7.4. and this portion comes out to be L by 2 tan theta. Now this ridge rafter length either you can find by this one by Pythagoras theorem, or directly you can do it as here you can see L by 2 cos theta, okay, or the Pythagoras theorem, and you will get some values. Now this nodes, let me zoom it, and these are the nodes. Okay, these nodes, one, two, second node, third node, these are at equidistances. Okay, these nodes are at equidistances, but these nodes are not at equidistances. Mind that. Keep in mind, these nodes are at equidistance, but not this one. Okay, so if you have to calculate this node distance, so length of rafter, distance between each nodes will be length of rafter 9.64 divided by 4, because 4 parts are there, 1, 2, 3, 4. Okay, you'll get 2.41. Now to calculate the distance of these nodes, okay, these nodes, suppose here it's x, here it's x1. We know that this is creating a right angle triangle. We know this length is 2.41, each member length. We need to find this length x. We have this theta, so cos theta will become 2.41 by x, so we can find x. Similarly, if we consider this triangle, we'll get x1, so x1 will become 2.41 into 2, this whole distance. Okay, this whole distance, and this distance we need to find, so we'll get x1 with the help of that. So we'll get this node, and all these four nodes are the same, and the symmetry follows here, so I'm not showing it here. Now let's come to our stad. Okay, so this is my file. Actually, let me open a new file, new. So name your structure here. Okay, and just very important is the units. English means it will come in kilopounds feet, pounds per feet, but in metrics it's Newton meter, so keep it here, Newton meter. Okay, now create. It already exists, so I'll rename it as truss. So create it. So this interface you will get. Okay, now creating the nodes and all is very simple. Let me go back to again PPT. So as I have said that we have to start from here, this point. Okay, this point we have to start. This will be our point 0 comma 0. Okay, and then we need to follow the same geometry, and coordinates will get, we know the coordinates from our calculations, and just we need to point that calculation coordinates and just join. So here you could see add beam, sorry, first node we have to define. Okay, node first is 0 commas, okay, it has been created. See, this node has been created. Okay, the second node is at a distance of here 0 comma 7.4, 0 comma 7.4. Okay, so let's this viewing, okay, it's still in 2D mode, so you can't. The third this one node will be here. Suppose this is 18 comma 7.4, 18 comma 7.4. Okay, and the fourth node will be at 18 comma 0. So you could see these are in I like this, since this x-axis is in towards the plane. So for this we can go to the view, we can change the view. So now you can see this is the x, this is the y. So four nodes, 1 2 3 4 nodes are created. Okay, so now add beam. This is very simple. Go to here, add beam, go to the joints, add beam. You could see here the cursor with a beam. Okay, beam. Okay, again a beam, again a beam, and similarly We have done this one. Now for let's define a middle node for this one, middle point. So for that, here you could see insert node. Okay, add midpoint. It will create at the midpoint. So you could see here it's created at the midpoint. Now one more node you have to create. This is this node, the topmost ridge. It is at 9 comma. Suppose I have some values. Suppose for me it's 9 comma at a distance of 13.4. Okay, so let me see what's my value. 10.854, 10.854. But keep in mind that this will be differing for everyone, so just don't copy the values. Okay, so here you see we will get a node here. Now let's add beam to this, to this, to this. Okay, okay, so we are done with this. Now we said I said that we have to divide this into four equal parts. Just insert nodes, add endpoints. Okay, add 3 points because here there are 3 points, 1 2 3 points. Okay, 3 points, 1 2 3. So 3 points, add endpoints, apply OK. So see, you get 3 endpoints. Similarly for this part. Okay, now let me complete one part. The other part will be same as above. I'll just do all the calculation, what to say, dead load, live load on one part, because why to just waste time. The other part you could just replicate of this. Okay, now let's do it. Okay, so let's add. We need to uh, add a node here actually, since we have calculated the distances by geometry. Okay, I have shown here how to calculate distance. What is it? Yeah, I've shown you here how to calculate the distances cos theta 2.41 by x. So with the help of that, I will be going to my stat and insert node. Okay, at a distance. Suppose my first point was 2.581, 2.581. Okay, add new point. Again, the distance is just the double, 5.163. Okay, add new point. Okay, okay, so yes, see here you could see two nodes. And one more thing I would say, just see here, you are seeing one. See, one green line, one red line, and one at the end you are seeing a blue line. So green line indicates the start of that member. Okay, and blue line means the end. Okay, so that if you're assigning any node, it's from starting from here. It will start from here. Okay, and it suppose I have given now right now 2.815. If I have to give from this end, then I have to subtract, like this is 9, so 9 minus 2.851, because this is the far end. Because see here it's showing, because this is a blue, so this is the far end of this entire member. So I have to start from here, the other way around. I hope you understand. Okay, so keep in mind that that thing, and let's now attach. Now one more thing, we have to add a midpoint here. Insert node, add midpoint. Okay, now start adding beam. Okay, let's start adding beam. Okay, undo it, add beam, add beam. Okay, add beam. Add beam, add beam. Oh, there's something wrong. So I have done a mistake here. We should not add the internal load here. I went wrong with the configuration actually. So let's add beam. Okay, so this one goes here, this one goes here. Okay, now I have to add a midpoint for mid node for this member. Okay, right now we can go forward. Okay, add beam. Oh, I've done a mistake. Let me go back. Let me. This node's right. I have assigned the nodes. So I've done a mistake in this part actually. I had to assign 3 nodes and I have assigned 4 nodes instead. So let's go with this part. Okay, insert node, add endpoints, 3 points. Okay, add endpoints. Wait. Remove. Add endpoints. Now this is perfect. Like I think I have clicked again and again. So yeah, I've got 4 members. Just forget about this part. I'm going to deal with this. Now for this lower part, see, this is the ending part. Okay, since this is the ending part. Okay, so for creating a nodes here, I have to go the other way around. Okay, so now let me do it. Insert node at a distance of, it was 2.851. Now it's 9 minus 2.851. So what will be that? Let me calculate with my calculator. 9 minus 2.851. Okay, so it goes to 6.149. 6.149, and add new point. The second point will be 9 minus, it's 5.163. So this is 3.837. 3.837. Add new point. Okay, now see, since this is the start of the beam, this green, so it will start giving values from here. So when I say 10 minus 2.81, so it will give this value up to this node. When I say 10 minus 5.63, it will create this node. Okay, so it's that way around, but in this member you can directly give 2.81. Okay, now let us add a beam. Add a beam here. Okay, we'll add a beam here. Okay, now for this major sling, I will create a midpoint. Add midpoint. Okay, now add point. I will create this. I will create this. I will create this. I will create this. Wait a minute. Is it correct? Yes. No, it's not. This geometry actually, it's like, it confused me a lot. It's just nothing but an M shape. Okay, M shape with one line here. So this is called as Fink. Okay, this is Fink 1, this will be Fink 2. I made a mistake in this part, so forgot what I said here. Just follow what I have dealt here. So okay, so similarly this will be mirror image here at this part. Okay, so now let's give the loading actually. Supports. So create support. So this is fixed support at, okay, this is fixed support. Add support. Okay, use cursor to assign, give here it a load, give it here a load. Okay, you're done. Close. Now we'll go one by one. Geometry, properties, materials in a chronological order. Properties. Now I'm going to add sections actually. So let me start with the sections. So selection database. Yes, I have my section database. uh, I will be going with the Indian standard because we are following our Indian standard. And first I'll be starting with angle section. So this is angle section, and we'll go with ISA 100 into 100 into 8. So come down, come down, come down, come down. Here it is. Yeah, ISA 100 into 8, and this will be long leg back to back double angle. Okay, long leg back to back double angle with a clear spacing. This is nothing but our the gusset plate length, because there are two angle, okay, two angle which is spaced at 0.1 meter, which I have shown you here. What is, see, this is the spacing. Okay, 0.01 meter or 10 mm. Okay, this is what I have given here. So add. So for gusset plate thickness should be constant, right? So this is one of the member. The second member will I'll choose as ISA 75 into 8. 8. 8. Okay, same long leg LD. Add. Added. You could see here everything being added. Now we'll be choosing ISA 50 into 6. 50 into 6. You cannot go beyond 50 the width and 6 thickness, because that's the minimum value. So you cannot go beyond this. So we are choosing this. Okay, add. Now we'll choose single section. We'll choose single section for our minor members. For that we'll choose 50 into 50 into 6, ISA 50 56. Add. Now come to, for the columns, come to the S shape. Okay, here we'll be choosing ISHB 450. Okay, ISHB 450. uh, ISHB, yeah, ISHB 450. It depicts Indian standard heavyweight beams. H means heavyweight. Okay, LB means lightweight, W means wide flanged beam. So 450 denotes the depth of the beam. So this is ISHB 450. Okay, add. These are the for the columns. So here we have described it. Now let's start giving it. Now this is the first one is for the ties. Okay, so assign, use cursor to assign. Not use cursor to, go back to properties. Okay, let's choose this entire tie. Okay, and choose this. Okay, again choose, we have to select it. We have to select it first. No, first we have to select the material and then this member, because this is for And the ISA 100 is for ties. Okay, so first we have to select and assign to selected beam. Assign, yes, could see here. Okay, similarly you could go back to this ISA. This is for a rafter plus major slings. So this is the rafter. Okay, rafter. Okay, and this is the major slings. Assigning. Okay, similarly this will be for mm, a major strut. Okay, major strut plus central beam. Okay, and next things will be, I'm not going into that. I'll go with the columns. I'm choosing this. Okay, assign. Yes, assigned. Now one thing, for this ties for this ties select this ties, this one, the beta angle. Okay, create beta angle and keep it as 180. I'll not discuss why it's 180. If you want to know it, just uh, contact me and I'll explain why it's 180. A sir has explained it in the class. So assign. Okay, select first. Remember to select first. Okay, now assign. Okay, beta angles. So we are complete with the section. Then after section we might go to the specification. Specification, materials. Okay, so put it as steel. Okay, for select for everything. Okay, steel, select everything. Assign, yes. So this you have to assign first, so that take the property of steel. I have not assigned many things here, the section. You do the same thing. Okay, so for specification, now come it to the beam. Come to the beam, come to truss. Okay, add truss. Okay, member truss. Now select this part, escape part. First select only this part of the truss and hold the members. If you have to select multiple parts, uh, select control key and then start clicking. Okay, don't leave your control key, press the control key and select multiple members. Okay, and then assign to selected beams. Assign, yes. So this means this stat understands that we are assigning it as a truss and it will take only axial forces. It will not induce any shear force or bending moment. Okay, now supports we have given. Okay, to supports we have given. Now comes the loading. Okay, so the geometry is done. Okay, not doing it with this part, and this part also have something I've left with the properties. Okay, you could add it here in the similar fashion. Now supports, let me come to the loading. Yes, so not here, load cases. Okay, generally, now come to the PPT. Yes, now let's come to the loading. We will be first discussing about the dead load and the live load. Okay, so dead load will be due to the self weight of galvano sheet. The sheet will be at the topmost layer, and then the purlins. The purlins will be this members, like this lateral members, which will be resting upon the rafter. Okay, then weight of the bracing and connections. Left weight of the bracing and connections. Now, first let us understand what's the influence area of any node. In RCC project, sir has, like we have did that, the influence area for any a column, like the half portion from each side, okay, that will be influencing at that particular column. Similarly for the truss member, suppose this is my, suppose this is my node, this is my node. So for this, the influence, this is the central node, okay, this is one truss, this is other truss, this is the other truss, okay, this is the isometric view actually. So each truss is spaced at 5 meter, 5 meter, okay. So for this node, a half distance from here, half distance from here, and then again half distance from here, half distance from here. So this length we have calculated that, this length we know that this is 2.34, okay, rafter length by 4 we know that, and this is s by 2, this is s by 2, so the total length become s. So for me it's 5 meter and this is 2.34 meter. So influence area of the central node, okay, central node it is, not the end nodes. So for end nodes, it will be just half the area of influence. Like, see, if this is the uh, rectangle, so this is for central node, okay, but for end nodes we'll be getting only up to this much, we'll be getting only this, okay, sorry, not like this, it will be, this is the end node, so we'll be getting only up to this part, okay. So due to that, this will become half of them, okay. 5 will be there, okay, 5 will be there, but it will be 2.34 by 2, okay, 2.34 by 2. It will be, I guess, like this half pura length, this will become 2.34, okay, this will become 2.34. So that's why this shoe, when we are, shoe means the end node, because it's at the bottom, that's why we keep it as a shoe, name it as a shoe. The load will be p by 2 at each central nodes, it is p, okay, at each central nodes it is p, and at the, for dead load and live load, for the ridge node it will be p, but for wind load it will be p by 2, okay, p by 2 from this part, p by 2 from this part. Since for dead load and live load this part is symmetrical and this part is also symmetrical, so we are considering that this will all be also p, but here at the end shoes it will be p by 2. Now let's come to the dead load calculation. So here our dead load, it is, for galvanum sheet it is thickness 0.5 mm with unit width 60 newton per mm square. So 0.06 kilonewtons, it is here newton, it is here kilonewton, multiplied by the influence area, here is the influence area, will give us the load. Now weight of purlin, now purlin is a straight member, so it will just contribute in terms of lengthwise, influence length. So 120 newton meter is the density, 5 meter is the, this one, the total influence length, so we'll get 0.6 newton. Now weight of bracing and connection, again 100 newton per meter square density multiplied by influence area. So this is the total dead load, not the total, but due to excluding the self weight of the truss. Now for self weight of the truss, there is some calculations which you need to write, okay. Here if I go to the seniors project, okay, sir has said to calculate the self weight of truss in this manner, but in stat pro we are not going to do that. Self weight will be calculated by stat itself. So just calculate this dead load. So here I'm getting 2.528. This is P. Okay, P value is 2.528. So at shoe I'll be getting P by 2. Okay, at shoe I'll be getting P by 2. And okay, now come to live load. Now for live load we have to see plan area. Okay, plan area. This is the plan. So for live load, this is the formula actually. Don't ask me how this comes. Sir has explained it in the class. 0.75 minus 0.02 into theta, which is the pitch angle given in the data sheet, minus 10. Okay, and such that it should satisfy that live load is greater than 0.4 kilonewton per meter square, and that will satisfy for everyone. Now for me here theta is 21 degree, so I'll substitute 21 in place of theta. I'm getting 0.53, which is greater than 0.4. Okay, now let me tell you about the plan area of each node. See this, it is this node here, this node here, this node here. So the total length of this, half length of the span is 9 meter, we know. So it is dividing, this is the perpendicular bisector, nothing but. So in 4 equal part, so each part will be 9 by 4. Okay, each length will be 9 by 4. So this part becomes 9 by 4, and the perpendicular distance between two nodes will become this, nothing but the spacing. So 5 meter into 9 by 4 meter will be the influence area. Okay, influence area on each node. So here I'm getting live load as 0.53 kilonewton per meter square multiplied by the influence area, 9 by 4 into 5. So here I get 5.62, and similarly load on each shoe will become the half, it is 2.81. Okay, now self weight of the beam we will of the truss we will give in the stat pro command. Now here load case detail, add. Okay, type load 1, dead, dead load, add. Next is live load, live load. Okay, wind load we'll see later on. Now in dead load, click on dead load, add. Okay, factor -1 means the y-axis is, I mean, upwards, load will depict +1, and since our all the weights are downward, if it is downward, the all the gravity load, self weight, so it's -1 here. So self weight of the load. So add self weight already here, self weight. Now nodal load. Nodal load is here. Okay, nodal node. Why I'm saying it as nodal load, because this loads P, it acts on the P by 2 acts on the node. Self weight is on the entire truss. So what load I'm getting here? Suppose 5.962. So keep in mind that here I should write minus 5.962, because minus depicts downward. Okay, downward. So add, and one more is P by 2, so it will become how much? 2.981. So minus 2.981. 2.981, and keep, don't forget to write it here minus, add. Now self weight, click on self weight and select the entire part. Okay, elect. Now assign to selected beam, assign. See, the integrated mark changed to green signal means we have assigned. Okay, the question mark changed to green signal means we have assigned. Now come to this load. Okay, I think I've given a wrong load here. This was for live load. So okay, no problem. Just a random value I've given. No problem. Okay, suppose this is the nodal load, and use cursor to assign. So this is at this point. What's happening? Is it not assigning? Ah, yeah. The nodes 1, 2, 3, and for this one we have to click here. Okay, for 5.62 here. Similar fashion in this side also. So for changing this scale, suppose this is the part, go to left click, labels, scales, point load, just apply and see, just go for 2, apply, okay, see, close it, you could see the change. Okay, this has become small. Now if you go to this self weight, it will show you this beam. Okay, this will become green, that means these are not selected. If I go to this, means these are the dead load, this will become green. If I go to this is becomes blue. So in a similar fashion, for live load also we have to add such points. Here self weight will not come, instead Fy will come. Okay, here we have Fy, where it is, yeah. So load here is P is 5.962 and P by 2 is 2.981. So in the similar fashion you have to apply. I'm not doing it since it's the same process. Now let's come back to wind load. I'll discuss it from a senior's PDF. Okay, now the third calculation is about wind load. It depends upon area. So this location is given in the data sheet. For me it's Kanyakumari, and from IS code from clause 6.2.1, that is, this is the IS 875 part 3 2015. Okay, this will be a figure. Permits Kanyakumari, this portion LO. So basic wind speed VB will be 39. Okay, it will be 39 meter per second for me. So its VB is 39 for me. For him it's 50 meter per second. Now design wind speed, that is Vz, is nothing but equal to K1, K2, K3, K4, VB. Now what is this all thing? It's written down here. I'm not going to explain in depth, but I would say this K1, K2, K3 will be same for everyone. Okay, will be same for everyone. Okay, for cross check you can check the clauses which are mentioned here. Only change will be coming here. Importance for K4, that is for cyclonic region. In clause 6.3.3 table 1 suggests that if it's your region is beyond 60 meter of coastal area, then give it as 1. If it is within 60 kilometer, then put it as 1.15. For me it's Kanyakumari, obviously it's within 16 kilometer of the coast, so I'll put 1.15. Okay, so design wind speed will be K1, K2, K3, K4 into VB. So here I will be getting my Vz. Now wind pressure I will get in terms of mean ground level, that is 10 meters. So this is the formula, 0.6 into Vz square. It's a form of Bernoulli principle. From there we are getting this, and this is the clause. So you could calculate your Pz. Now for the design, this is the wind pressure Pz. Now for the design wind pressure Pd, we should take maximum of this Kd, Ka, Kd, Kc, Pz, comma 0.7 Pz. Now this, what is this Ka, Kd, Kc, Kc? This is mentioned here. Now for Kd value will be constant for everyone, 0.9, since it's a truss. Only difference will be Ka, that is area mean factor. Now when you go to area mean factor, you will be seeing that uh, a table will be there, table 4. Okay, let me show here. If I could scroll down, table 3, yeah, table 4, this is Ka. So tributary area, the tributary area for him it is uh, 33.81, but for like my case it was something different. It is nothing but the member length into the spacing. Okay, the tributary area. So this will be, suppose my member length was 2.4 meter. Okay, so 2.4 meter into 5, it is coming approx, for me it was something 45. Okay, so for that value, wait a minute, 9 point. So this tributary area is nothing but this part. What I would say is that this rafter length, that is for my case it is 9.64 into the spacing, which is 5 meter. So in this case for him the rafter length is 6.769 into the spacing 5 meter. So he is getting 33.81. Now come to IS 875. Now tributary area lies between 25 to 100, and now you have to interpolate your values and get it. He is getting 0.88 in this. So this Kc combination factor, it will be 0 0.9 for everyone. Only change will be coming here. Okay, here Ka and here K4. Okay, so this is about the calculation of this one. Now, okay, yeah. So design wind pressure will be maximum of Ka, Kd, Kc, Pz, or it should not be less than 0.7 Pz. So do it this one calculation. He gets this value maximum of this. Okay. So this is the design wind pressure in terms of Newton per meter square. Now calculation of pressure coefficients. So this is the important part actually. What it is. Now let's come to first table 6. Table 6 is for pitched roofs. So we are designing for truss. So this is the table 6. Okay. This is table 6. Now for calculation of external pressure coefficients, okay, CPE and CPI. Okay, to calculate a CP net we need CPE and CPI. So for that first we need to have H by W ratio. Okay, H by W ratio means this is H and this is W. H means from the ground level only. Okay, if it's given in your data sheet as 8, then 8, and width is suppose the span. So here for him H by W is 8 by 13, which is 0.164. So it comes in the second, this one, between 1 by 2 to 3 by 2. So he will go with this. Okay, he will go with this row. For me it was less than 1 by 2, so I will go with this row. Okay, now roof angle. Roof angle, it is variable for everyone. For him it is, roof angle is how much? Yeah, for him it's 16 degree. So but it is between 10 degree to 20 degree. So he will go for 10 and 20 degree, and he will interpolate this value for 0 degree and for 90 degree. Now what is this EFGH? Okay, for that let me come to this. This is nothing but, suppose this is the isometric view of your entire structure. Now when we see the top view or the plan view, the top portion will be like this. Now let us consider only the half portion, because this is not, will become the symmetric. So this half portion is divided into 4 quarters. This is EFGH. Okay, and this side, the windward side, is called as the wind is coming in. At IS code there is only two provision: the wind is hitting the structure, which is at 0 degree, and which is at one is at 90 degree. But since we know that our wind is coming to the roof, which is in inclined surface, so it will be neither 0, so neither 90. So for that purpose there are these coefficients. Okay, coefficients of pressure. So for EF and for GH we are having, okay, EF is one side, GH is one side. And for when it comes to 90-degree, it will be EG and FH. Okay, EG and FH. So you could see here, he has interpolated all the values, okay, and he got the CP values. Okay, these are the CPE values, external coefficients of pressure. Okay, external coefficients of pressure from table 6. Now there is another factor, that is internal pressure, because due to some openings, in the walls, it's not drawing. So due to some openings in the walls, suppose this is some opening, and wind might come inside. Okay, wind might come inside, so it might create some pressure on the walls. Now before that, I'll say what is this plus or minus. Plus minus means, now it's, let us say this is the top sheet, the top roof. So this minus means suction pressure. Okay, it is sucking, so this is creating a suction. So this is from away from the surface. Okay, here it is, hence value coefficient positive means away from the roof sheeting, and negative means towards the sheeting. Okay, so 0.86, see here, for this zero angle he has 0.86, so away from the section. Similarly for CPI, it will be plus or minus 0.5 for everyone. Okay, because that comes in tributary area 3. What is that, I will explain later on. Okay, but it will be same for everyone, that is CPI will be plus 0.5 and minus 0.5. We have to take both the cases. Assuming the opening of the building is between 5 to 20%, this opening, so value of CPI will be this and this. Now first we are taking positive 0.5. So you might think that this, it is acting the same direction of this, so this is also should be negative, but it's not like that. If you see from the top surface, this part, it is going away from the surface, away from the sheeting. And from inside, when you see from the inside, when you see, from inside, you will find that this surface is hitting, okay, hitting the roof, so this becomes positive. So this will add up. Okay, no, sorry, not this will not add up, this will instead, uh, yeah, this away from the surface, this is away from the surface, so 0.86 is away, and this is also 0. Okay, CPI, yeah, net CP is equal to CPI minus CPE minus CPI. Okay, here will be the formula of that. CP net is equal to CPE minus CPI. So 0.86 minus of 0.5. Okay, minus 0.86, it is minus 0.86 minus of 0.5, so it will become minus 1.36, minus 1.36, that means it is away from the surface. Okay, similarly here also, it is 0.54 and this is 0.5, therefore 1.04. Now the case 2 comes as angle, for same zero angle it will be CPI minus 0.5. Now here's, now when you go for CP net, it will become minus 0.86 minus of minus 0.5. So it will become minus 0.86 plus 0.5. So it will be minus 0.36, that is away from the surface. 0.36 but away from the surface. Similarly, again we'll take case 3 for angle 90 and CPI positive plus 0.5. Angle 90, CPI minus 0.5. So these are the four cases actually for wind load. So which we'll be depicting, we'll be uploading in the STAD. Okay, now for loading, the force will be CP net into area into PD. Okay, CP net into area into PD. So this CP net is nothing but CPE minus CPI. and area is nothing but area of one member, that is distance between two nodes, that is rafter length by 4 into 5, okay, the spacing. And PD we have calculated above. So see here, CP net for load on each, for case 1, each intermediate node 1.36 you can see here, 1.36 you can see here. So 1.36 into this and this much node, and this is suction. Even though he has not indicated minus load, but he has written down here suction. Suction means negative. And similarly, at end and top nodes it will be by 2, okay, by 2. And for GH portion it will be similarly in the same fashion it will be there. And this will be the various cases, case 1, case 2, case 3, case 4, you will be getting the loads. Now calculation of load on column we don't have to do it right now, we have to do just till here, okay. And this part is also should be omitted because this is for frame, okay. This part also should be omitted, we should not do this, only up to here. Again don't know this, again start from here and end it up to here, okay. So we have got various sorry, you have no columns should be included, end it here. So you will be getting loading on different members due to wind load. Now how to give wind load, I will say tell you. Now again, load details, add member 3 possesses wind load, WL WL1, okay, add, then again WL2, add, because there are 4 cases, so every case will give rise to 4 kinds of loading, WL4, okay, close. Now since sir has said to do up to class 9th February, okay, so you could do the calculation up to wind load, okay, because sir will I think explain it in the next class, okay, or he has explained in the 19th February class, 16th February class. So this wind load, how to give that, and I think it's not necessary right now to explain you. If you want, you can contact me how to add this wind load, because the video is getting too lengthy. So till that, add up to the live load. Okay, do the analysis. Okay, first give it as steel with IS 800 2007 LSD. Okay, anal complete analysis, do it all, add, close, okay, analysis steel, okay, then put some parameters, define some parameters, all, add, close, okay, define commands, not here. Oh sorry, first you have to select the whole member, define parameters, where is the FU, not getting it. Now let me come out of that project, because till that do it up to live load, okay, and submit till that, and do the calculation, manual calculation of wind load, okay. No need to do it in STAD right now, sir will explain it, because we have to submit it up to 9th February. I'm just showing my project file, So this is the loading which you have to give. Like I have given up to wind load. So first dead load, then live load, then wind load 1. Similarly wind load 2, 3, 4 will be there. Okay, then again this will be combinations. So we will only deal with combinations. These are various combination. You will get 15 combination like this. Okay, then you have to go for the analysis, perform analysis here. Okay, and then you have to go for design, and then you have to do some check codes, and you have to define some parameters. Okay, you have to define some parameters such as fu, yield strength, and sorry, ultimate strength and ultimate yield points. Okay, and that will finish it up to the wind load. But this is just for information purpose. You have to do it up to the live load only. Okay, for stat sir will explain the wind load, or you can see it in the 16th February video, and he'll be explaining the rest of the part in tomorrow's class, or today's class. I would say it's already 12. So yes, complete it up to here. This is the manual calculation, and stat up to live load. Okay, stat up to live load. If you want, I'll attach this PDF, or you can find this PDF from being civil. Okay, you can find this PDF from being civil. So that was all from today's video. I hope this video has gone so long, so it's being so late. For that, apologies. Thank you.